first thing, I want to thank you for being out there teaching our younger generations. That's very important work, and I know from my experience that in your positions you really have a lot of impact on these kids. I had some teachers that made a big impact on me growing up without me even knowing it or realizing it, because I went into undergrad as a political science major. I had no idea that I was interested in science. I think my parents knew, but I ended up in engineering, and looking back, my 8th grade science teacher had a big impact on me, and as well as my calculus teacher. So thank you, and keep it up. But I also want to say that before my list of degrees scares you off of this kind of career, I want to say it's not necessarily a prerequisite for this type of career. It certainly helped me get my foot in the door, and especially I'm getting the experience. I will eventually be an expert witness. That's what my firm mostly does. So, of course, in front of a jury, a PhD looks good. But there are a lot of support roles that go along with it, and you don't have to have advanced degrees for those. There's also, if somebody goes out and works in the industry for 20 years and then is an expert on widgets, then they can do this kind of career too, and it's very respected. So, with that introduction, I'm a senior staff consultant for Engineering Systems Incorporated, ESI. It's kind of the vaguest name ever. But our tagline that we like to use is engineering and scientific investigation. That gives you a little bit about what we do. And it really runs the gamut. My particular area of expertise is explosions, but we do anything from aviation, so plane crashes, to roofs, like tiles on roofs. We'll investigate those if they failed in some way. So we have a lot of different disciplines, and that's what makes it exciting. Any given day I'm working with a number of different consultants across my company, which is across the country, on a bunch of different projects, and it's fun. Okay, so this is the list. So bachelor's, I did all my degrees in mechanical engineering. So bachelor's from Texas A&M, and then master's and PhD from Colorado School of Mines, A&M. Colorado School of Mines, I basically got in there, was intending on doing a master's degree, and got in there, loved my project so much that I decided I wanted to do a PhD. My husband wasn't necessarily excited about that, but I think he's fine with it now. And my PhD was in solid oxide fuel cells, so alternative energy, and I really got into chemical engineering with that because I was looking at the chemical reactions over the surface of a solid oxide fuel cell. The benefit of one of those fuel cells is that it operates at 800 degrees Celsius. So a fuel cell that you might have heard a little more about would be the types that they were talking about putting in cars. Those are different. They operate at 100 degrees Celsius. So the benefit to the type I was working on is that they don't need pure hydrogen. They can work off of natural gas. There are some problems with natural gas and the byproducts that it produces when it goes through a catalytic reaction. So that's what I was focusing on. But I just loved it and built my experiment from the ground up, did a computational model with it, and ran with it. Had a lot of fun. After that, we moved back to Dallas, and I had a job working at a defense contractor lasted there for about 11 months, and decided that it wasn't for me. There are all types of engineering jobs. That was more of a design engineering job, and it just wasn't for me, but it is for some people. And I would definitely say that we were having a conversation earlier, what should kids be focusing on? What I see in what I saw in that job, what I see in this job now, the importance of kids developing an understanding of visualizing things in 3D, I think is huge. There are a lot of 3D technologies out there. The design software is all 3D modeling software. Some of the tools that we use end up being like 3D laser scanning and CT scanning. So we're working with things in 3D, and it really helps if they can start developing an intuition for that. Then began working at ESI in May of 2013, and I'm in the Fire and Explosions practice group. But I'm also young, and it's kind of like at a law firm where the young ones do all the grunt work. But that's how you get experience. Okay, and this is just a snapshot of what I've worked on. I've worked on everything from air conditioner coils, evaporator coils, a lot of them, to a large-scale industrial explosion at a petrochemical plant. What I'm doing in any given day, so say we'll take this air conditioner coil project for example. I have spent a lot of time behind Excel, just dealing with all of the data that we have on it because we did tests on a bunch of these. So I've just become the master of the Excel spreadsheet, and then working on ways to present, because my client, actually, I suppose I should back up. Okay, so my firm does failure analysis consulting. Most of our clients are lawyers. So let's say something happens, there's an accident, there's an explosion, all the lawyers get involved. They come in, they all hire their own experts to start, so people like us, to start investigating what went wrong. There's a lot of not necessarily games that are played with that, but you go in, you come on the scene, and you just start gathering information. And you'll probably have other experts or other parties, other experts, other lawyers there at the scene with you. And you all have to kind of agree on what to do, what evidence to take. We take a lot of photographs, so a ton of photographs. My wrist gets rather tired sometimes. But take a bunch of photographs, agree on what to take. Then after that, you agree on what you want to look at closer. So then you'll probably take that into a lab setting. Sometimes it involves, like with this one, this is a really large heat exchanger, so it involved a lot of cutting out at the site. Then we moved all of those pieces to a lab somewhere to cut them down smaller and smaller and smaller, and it ends up getting to the microscopic level by the end of it, a lot of these things do. So that back up and give you a broad overview of what I'm doing. We also have some industrial clients too, like people will call us up if they're looking for help with some of their processes. Maybe they're considering switching their processes, and they'll call us up to help them investigate and decide on what the best option is. But so back to my day-to-day. So I could be spending the day behind Excel and then talking to the client. Communication skills are really important because the lawyer, some of them, the ones that are easier to work with, have a bit of a scientific background or an engineering background. Some of them do not. So you have to take it down to a level where a lot of people will understand it. And then if you're talking about something that might go to trial, then you have to start thinking about it from the lines of what would a jury understand? Because it can get pretty complicated. This one right here came down to on the weld surface. There were a few at the points of initiation. There were a few tiny little thumbnail cracks within the material that we looked at. So got down really small, and it's just hard, like keeping track of and taking somebody through. Okay, we took this huge object that used to look like this. Now it looks like a taco shell. then we looked at the edges of it, started cutting, and then we cut some more, and that's where we get to this that looks really big in the photograph, but it's really not that big. And it actually turns out that it didn't make a difference, that this thing would have failed either way because of the events that occurred. A lot of times there's human error involved in this, so we go in and try to figure out what was human error, what was maybe not human error, what was maybe like a defect in the product of the end. Okay, and so a large part of what we're doing, we are always we want the truth. I think there are some people out there who think that we just tell clients what they want to hear, but we do want to get to the bottom of it and get the truth and tell our clients what it is. Sometimes the good clients are happy that we gave them bad news. I mean, they're not happy about the bad news, but it helps. So the first thing to do is identify the problem. So what failed? Then define the problem. This failed on such and such day. There are all of these factors that could have contributed to it. We need to go in and start figuring out which factors might have contributed to it. So, and collect data, take photographs, collect evidence, do a 3D laser scan of the scene. That can be extremely useful, especially in something, in a case like that, where actually this case is really interesting. You can go on the Chemical Safety Board website and pull that from it. I'm not recalling right now the name of the place. Oh, NDK. NDK in Belvedere, Illinois. When this ruptured, they were making, I think it operated at 50,000 PSI, which is really, they were synthesizing crystals. So this was fired up at 50,000 PSI, and they had some stress corrosion cracking in their vessels that they had recognized as a problem. Like they already knew it was there. And actually, they had hired ESI in years previous to look at a problem that they knew they were having, and we had sent them a letter that said, hey, you have this problem. If you don't go and investigate these pressure vessels, this is going to happen. And it did. Like we actually said, hey, this pressure vessel, it could explode, and the tollway oasis that's across the highway is in jeopardy. And when it exploded, the trucker was walking back to his truck, and he was struck and was killed as a result. So it's kind of, you develop a weird sense of humor in this kind of business because you have to. But if you go on, if you're interested in any of these types of events, maybe you want to teach your students about it. The Chemical Safety Board website has a lot of published incident investigations, and they even have some videos where they'll take you through it and leave out all the nitty-gritty, so it's a little easier to digest. Sorry, I'm not hinging there. But so collect the data. I was talking about 3D laser scanning, which is really useful in a case like that, because after the fact we can go in and do some simulations, do some calculations to understand the blast radius. But a really important part of that is having data to link that back to, so that you know that your model is correct. Otherwise, you put junk in, and you're going to get junk out. So analyzing the data, that would be in the lab afterwards. That's when we're talking about cutting things and looking at microscopes, doing CT scanning. It could be running calculations, also be researching standards. I think I get into this on the next slide. But develop hypotheses. So develop a bunch of however many hypotheses you need to understand, I think that this failed because they overpressured it, or I think that it failed because there was a problem with the material. And then you go and test those hypotheses with calculations, with simulations, by looking at things under microscopes. They can even be thought experiments. And then go through all of that and select the final hypothesis or the most probable cause for the incident. A lot of times there's some gray area. So really when we're talking about being in court, being deposed on something or writing a report, then we want to be, we want to have a reasonable degree of engineering certainty that something happened the way it happened. And I think that threshold is technically 51%, which seems, I'm not comfortable with that. So I think we all have our own comfort level of what we will testify to. Tools and techniques, I've mentioned some of these. Photography is huge. I'm really good at taking pictures of small metal objects. And I would really like to get good at taking pictures of people or something someday. Measurements. Measurements are huge because, like I say, Doug, you go into a fire scene or something and you need the layout because you might need it later. So being able to take measurements really well, sketch them up is very important. And that's actually a part of this job that would be good for somebody who doesn't necessarily have an advanced degree, but really good technicians, people who are really good at taking measurements or really good at doing 3D laser scans. That kind of job is very important. Non-destructive testing. So a lot of times we will, the first step in the investigation is to go in, document the site, take the evidence. Then we will all get together and agree on non-destructive testing that we want to use. That would be more photography. I mentioned CT scanning, and I can show you a video of that real quick. We actually have a CT scanner in our Dallas office. So this is an aircraft carburetor. This is just the digital photograph that we have from it. And it morphs that data from the CT scan that we did. So you can see the outside body of it. And then we strip it down to the interior components. And on these aircraft carburetors, a big item of interest is the float. So this is the part in the carburetor that controls how much fuel is allowed to go in and out of the engine. And they were having trouble, and that's the valve seat. So there were a lot of problems with these when they were made from a different material because they were actually made from two different pieces and they had a seam in them. And that seam would leak and cause the float to fill with fuel. So then the carburetor wouldn't function correctly, it wouldn't get the engine fuel when it needed it. And then they caused some accidents, and they changed to a foam float. So now that problem is fixed, but it doesn't get fixed without really digging in and getting to the nitty-gritty of why this stuff is happening in the first place. So the beauty of CT scanning, have any of you had a CT scan done medically? Yeah. So an X-ray is great. It gives you information. Like, take an X-ray of my hand. I get all of the 2D information, all of my bones stacked on top of each other. If you take that and rotate it, take another X-ray, you get a whole other set of information. So then, the principle of the CT scan is you actually take it, rotate it 360 degrees as you're taking X-rays, and then use a computer algorithm to put it together into a 3D model. So that's when you can start digging into components and cross-sectioning. Difference between a medical CT CT scan and an industrial CT scanner is that it's a much higher power, so you don't want to go in our CT scanner. But also, instead of, fortunately with a medical CT scan, we're stationary and the source rotates. The part you put on the table, it rotates around. So fortunately, we don't have to do that. Okay. Okay, so some of the other things I end up doing, well, after we do non-destructive testing, then we'll start cutting things apart, doing more destructive testing. I also do a lot of research on standards, product manuals, and literature, so it's a lot of reading and using my Google skills. Those are very important. Documentation review, digging into a company's past documents. Sometimes they can come in stacks of 50,000 documents, and that's where I'm talking about the young people do all of that good work. Calculations. A few weeks ago, I was doing a leak analysis calculation, so just really digging in and getting to the bottom of that. Computer modeling is another thing. And then also experiments with what we call exemplar components. That would be so if we were looking at that carburetor, we had the one that was involved in the crash, but then we get a new one, so we know what the new one is supposed to look like, and we can do we can cut into that one. We can do whatever we want to that one without having to tell all of the lawyers and other parties involved. Okay, see how I'm on time. Okay, so real quickly, I'll just go through this. So this was actually an explosion that occurred in someone's barn. This component right here was a heater that was on the wall, and it was actually installed shortly by the owner of the property right before the explosion. So that's a clue to go in and just put that in your feather, or put that feather in your hat. And then, you can tell from this, a lot of times you go in and you're just like, okay, where do we start? So this piece right here was actually they didn't really pay attention to this at the scene, because there's so many things to dig through when you're out in bad lighting. They identified it later as being a very important component, so it's a very good thing that they actually got this in the picture to begin with. But this one ended up, so this was the connection to the space heater, the natural gas connection. You can see here, I think actually it's this tube down at the bottom. So this valve went into this heater, and then this tube had pulled out. Now, there's a fire, there's an explosion. A lot of things happen during the course of an explosion. So, a lot of the key questions that we're left trying to answer are, did this happen before the explosion? Was this an event that could have caused it? Or did it happen as a result of the explosion? Actually, just yesterday, I was in Baton Rouge for a lab inspection where we're looking at all of these different components from a well that was involved in it. There was a fire, and they had to just let it burn for 2 weeks. So there's a lot of damage on those components, and we're trying to figure out, well, are these threads damaged because they were in the fire, or are they damaged and that might cause the event? But there's some gray area there. This was the component that they ended up focusing on in this barn explosion. So, upon looking at it, they compared it to a standard. They said, well, this doesn't really look how we would expect it to look. So if you look here at the edges, it looks like it could have been pulled out. So they did a CT scan. They took 3 exemplar ones. They made one that was per specification, CT scanned that. They made one that had the flare that had been pulled out, CT scanned that. And then they made one that didn't have a flare actually connected, the connection was never made. So this one right here, this one actually has a leak path. And this is what the subject one looked like. So by doing that, they were able to determine that that was the sequence of events that caused the explosion in the first place, and it was just an improper installation. Unfortunate. Okay. So, I'm not really going to cover Deflategate, but, just because that goes into some nitty-gritty, nitty-gritty that I didn't feel was good for the time period. But that, have any of y'all looked at that? There's some classroom, I briefly Googled it, and there are a lot of like classroom, people who put together classroom demonstrations on it and stuff. I think that would be really fun to do because you can teach them, it's all based on the ideal gas law. Right? Increase in decrease in temperature causes a decrease in pressure, but it comes down to how much that temperature decreased and whether or not the footballs from the 2 different teams had a decrease in pressure at the same rate. So that's what, but I won't comment too much on our competitors' methodologies for doing the experiments they did. But I have, this is just a really simple example, but I have this football here. So, does anybody want to give me some observations on this football?
Smaller than the other one.
Almost square.
Smaller than the other one. Smaller than the other one. So,
This seems
yeah, that's
Easier
a
to
good
grip.
Easier to catch.
It is easier to catch. It's much
Easier to
easier catch. So, smaller than the other one, which means that there's less air in it. So, it might have a leak. Yeah, so any other ideas about what maybe could have happened to this? If it's not holding air anymore?
Might be punctured.
Yeah, punctured, that's a good one. That's a good one. What about,
the seaming or the stitching might not be there.
yeah,
The
yeah,
valve
exactly,
could
that's
have
good
failed.
too.
The valve could have failed.
Closed valve.
The valve could have failed, yes. Anything, let's see, what about, could it have been overpressured?
Yeah.
Overpressured.
And then caused a rupture.
Exactly, yeah, and what would you expect to see if it had? Yeah,
Wouldn't hold any air.
right, wouldn't hold any air, maybe these threads would have been stretched out more, there'd be more all over damage as opposed to what we have here.
Change of temperature could have changed the
It could have.
It was filled in a hot environment and it brought it to a cold environment.
Yeah, it could have. And then to test that hypothesis, you could think, so it's probably like 70 degrees in here. You can, depending on the size of the vessel, you can roughly say like 1 psi for every degree of temperature drop. So, I don't know, it says on here, inflate 7 to 9 pounds. So this might be, yeah, I don't know. This might be like 3 or 4 pounds or something. So, I don't know, maybe not. But, what we would do, so this is an exemplar. This is what it's supposed to look like. So I can take pictures comparing the two, and then I'll take you, I actually took this into the lab and took some pictures of it, so. Some of these pictures are bad, so just ignore that if you take bad pictures sometimes. Okay, so I would this is just kind of my typical methodology. Everything I start out, usually try to get a scale in there. Somebody pointed out on the Deflategate report that Exponent doesn't even know how to use a scale, doesn't even know how to measure things properly. But I'm not necessarily measuring this, like I'm not going to line up the number 1 with the end of it. I want a scale in there so that in case I have to go back to my photos later and measure the threads, I can do that because I can tell the software, like, hey, this is an inch here. So if this is an inch, how long is that? So that's why we like to have scales and things. Oh, this isn't going to work because it's not PowerPoint. Can I not click through these?
If you highlight all of them, then if you click on
Okay.
one, then you can go through.
Okay.
Yeah, if you just do Command A.
Oh, Command A. That'll be easier. Maybe.
Yeah, and then highlight one, the first one.
You guys still messed that up. Sorry, just not used to using a Mac. I have one at home. I'll let you do it. Okay. Thank you. Okay, great. Thank you. Thanks. Okay, so this is just an example. Another thing that we always like to do is take pictures of any markings that are on whatever we're looking at. So this one says, I know that it's an NFL football made by Wilson, and you want to inflate it to 7 to 9 pounds, and WTF. Great part number. WTF 1695. I mean, usually I'm extremely interested in model and serial numbers because that can help me figure things out later. You can also see the valve here. The valve in that photo, it appears to be in pretty decent condition, but we should certainly take a closer look at it. Just more pictures, lots and lots of pictures. Okay, so now just kind of looking at the threads. Might just go along here and take some photos. There's the valve. Doesn't look too bad. But notice something there? Not white. You want to look at it? Yeah. So that's what we would term an anomaly. Until we know what it is, we wouldn't call it a puncture. Yeah, not until we know what it is. So, just by observing, you can pick up a lot of clues just by paying attention. Measurements of the football, and then that's the exemplar. So then I took it, like, oh, that area looks interesting. So I took it under the microscope and started taking pictures of that area of interest. So you get closer. And yeah, so anybody know what happened to it? Because we have, so we have this under here. That's probably the interior of it coming out a little bit. this is the other side of it. So now we know, by observing the other side of it, we know that it's not supposed to look that way. That's basically all the clues I have. But that was just a little small. It was punctured. My husband took a. I was like, I need to damage this, so he tried really hard to make that happen. No, because we don't have an ice pick. I think he ended up using a flathead screwdriver. Yeah. Yeah, I wish I was like, need an ice pick. But that just gives you a little bit of taste of the method that we go through. Just looking, I'm almost done. Yeah, and now my dog will be very happy when I get that. Okay, so key skills that I think are important in any technical industry job, but math and science, obviously. I go back to, I actually had to pull out my calculus book the other day. Yeah, I was reaching. That was on that leak path analysis because I had to figure out, we wanted to know the leak rate through the screw threads of a 2-inch NPT fitting. And that involves some calculus to figure out that leak path. So inductive and deductive reasoning, basically applying the scientific method. Don't jump to conclusions before you have all the information, basically. Photography is a really good skill to teach, I think. Plus, it's just kind of cool. I mean, it's nice. It's a nice skill to have. Writing, we write a lot of reports, and then communicate. Every time we're going to do something to some evidence, we have to communicate what we're going to do, called a protocol, and then send that to the client. Also, oral communication. So eventually I will be deposed, like be in the deposition, so I do need to be able to communicate well and clearly to a jury and to lawyers, to clients, even over the phone too. I feel like, I don't know if y'all are with me, but I feel like kids probably these days are maybe a little bit intimidated by picking up the phone and calling somebody. But that's really useful to be comfortable with. And debate skills. That is something that I feel would be useful not only in my career, but in my career field, but also if you're in industry and if you gather all the facts, you are firm on your conclusion, you think that what you've decided to do is right. I mean, being able to express your point of view and think on your feet enough to really have a good, in-depth conversation with somebody about why you think the way you do and why you think the other person is wrong. All of that. Very useful. And then also, I'll go ahead, and I actually got involved with this tonight through High Tech High Heels, which is it's a local organization started by some women at TI, and it involves women in STEM career fields. Something that they do physics summer camps for girls. They also do a lot of training for educators. They've actually found that with girls, physics is the most, this is through documented research, physics is the most intimidating one. That's where girls get turned off of science. And I think back to my physics class in high school, I was intimidated by it. I don't know, I just felt like, I don't know if I felt like it was a guy thing or I shied away from participating in it. So they have some training that they offer to help teachers be more aware and more aware of techniques that can help make it a little, make it on equal footing a little bit. So you can check out that organization, hightechhighheels.org. They also supply, if you need speakers for a career day or something like that, they'll hook you up. And then This organization was actually based on this national organization, so you can also check out their website. I think they have some grants and different programs that they offer. So, and I think that one may not be just, I think that one's all types of minorities and STEM career fields. Okay, so that's it. If you have questions, feel free to contact me.